Hello and welcome to a small video on how to create Lewis structures. We'll talk a little bit about covalent bonds, a little bit about the Lewis structure process itself, and then we'll talk a little bit about exceptions to the Lewis structures. First of all, just to kind of review a few things, the covalent bonds of course form molecules, and this has lots of consequences as far as the molecules are concerned. They are very discrete. They have the exact number of atoms, so we use a molecular formula to describe that. For example, we could have C6H12O6. That is a very specific number of atoms for a very specific molecule. If you split it in half, you will not have glucose anymore. We're all sharing electrons in covalent bonds in order to fulfill our full outer shell. So I'm going to erase this for a moment just to give myself a little more room here. And when we share electrons, we can form single bonds, double bonds, and triple bonds. Now, ionic compounds do not share electrons. So if someone were to ask you, what's the bond between sodium and chloride? Is it single? Is it double? Is it triple? It's none of the above. It's not sharing anything. It had a transfer of electrons. This is the cation, this is the anion, and those should be electrically neutral. Either way, so single bonds share 2 electrons, 4 electrons, 6 electrons. A few things that we might want to know about. One is length, and it gets longer as you go up. So I'm going to have the arrow as far as increasing in magnitude as far as the length is concerned. So single bonds are slightly longer than triple bonds. Slightly, but they can be measured. So it's in angstroms, but they can tell the difference. Next up here we have what might be considered bond dissociation energy, or bond energy. Okay, and this increases as you go down. So triple bonds just involve more energy than do single bonds. This is not including anything involved with stability. For example, NH3 or N2 has a triple bond, and it is quite stable. The majority of our atmosphere is in this way. In class, we'll often show a chemical called NH3, Ni3. Nitrogen triiodide. This is all singly bonded, but is an extremely unstable compound. It will break down into 2 other compounds. One is going to be nitrogen gas, and the other one is going to be iodine gas. So this is triple bonded, this is single bonded. So just because it's single bonded doesn't mean that it is in fact stable, or just because it's triple doesn't mean that it's stable. Otherwise, things you might want to know about these things. We have a bond order as well. It's another numerical numbering system. They just say 1, 2, and 3 as far as bond order is concerned. A little bit about sharing of the electrons. Clicking to our next page here. How do I draw a Lewis structure? I have a list of a couple rules here that you would want to follow, and it really is very much procedural based. You could, after some practice, be able to follow these instructions and be able to complete a Lewis structure. It's not something where there's critical thought involved. You simply just have to follow the instructions. It does, however, give you a big picture view of how an atom is sharing electrons. It doesn't give you everything. It's a 2-dimensional drawing of a 3-dimensional structure. It's not giving any molecular shapes. It's just giving you a general outline, layout of the molecule. For example, water, of course, is bent. It looks like this. But nothing in our Lewis structure that we know so far, at least, is going to give us any indication that it's this versus this. Okay? Obviously, this is a better depiction of the molecule, but we just don't have enough to tell us how this works. So at this point, geometry-wise, I'm not too concerned yet. Erase that. Now, first thing, if we want to do, let's just say, electron inventory for water. H2O. I'll do it up here. We want to do a valence inventory. So these are the number, all the electrons that are going to be involved in the bonding or the satisfaction of the outer energy levels of both hydrogen and oxygen. Hydrogen has 1 valence electron, and there are 2 of them total for 2 electrons contributed by the hydrogens. Oxygen has 6 valence electrons for a grand total of 8 electrons. Now, this number, generally speaking, should always be even. Okay. Is it possible for it to be odd? Yes, but it would be extremely reactive chemical. Is not real happy. So even is our general rule of thumb here. The second idea we have here is called a skeleton structure. I'm going to hook everything up with single bonds. Can't have less than a single bond, so just get a general skeleton structure. Keep in mind that hydrogen can only bond 1 time. It cannot have any electrons around the outside of it. It has a very small atom. It's simply going to be used 2 electrons. Like I mentioned here, hydrogen only bonds 1 time, so we're going to separate our skeleton structure. Now, this item here, usually the first item listed goes in the center, but since hydrogen only bonds 1 time, I'll take the next item in line, and that will be the center of the structure. So just drawing it out here, dash, dash, hydrogen, and hydrogen with 2 single bonds. Again, I'm not showing any molecular geometry here. Now, on to step 3. There's my reminder of hydrogen only bond 1 time. No electrons for hydrogen. All right, so no extra electrons, just the 2 electrons here. We call it the duet rule. So next thing here, we're going to give out electrons to fulfill the octet rule. So this is the way I do this, so listen carefully here. I count 2, 4, 6, and then 8. Now, at this point, I have matched my full energy level for the full electron allotment for the oxygen. I have also, consequently, met this maximum, so I have to stop at this point. I cannot add any more electrons. Turns out that the hydrogens, of course, after bonding are fulfilled, and the hydrogen on this side after bonding is fulfilled, so everything is full. I am done with my Lewis structure. I have 2 bonded pairs and 2 non-bonded pairs. Now, the last 2 parts of the instructions say, what do you do if you don't have enough electrons? Well, in that case, we'll deal with that on the next example. And then what do you do if you have too many electrons? And we'll deal with that in a different example as well. So at this point here, let's try a second example. This particular example is in your workbook. It's the first problem of your workbook, and it is nitrate, NO3 minus 1. A couple of things we'll want to note here. First of all, this has a charge here. So I'll explain that in a moment, but be aware that there's a charge here. So let's start rule number 1, valence inventory. This is going to give me 5. This is going to give me 6 times 3 is 18. 18 plus 5 is 23. Now, 23 electrons, of course, is odd. This is not really allowed. You can't really have an odd number of electrons, at least not for our purposes. Add 1 more electron onto this thing, and we get a grand total of 24 electrons. It is quite common for a student to see -1 and to subtract an electron. Electrons are negative. We have an extra electron here. You must add an electron. If it was positive, I would subtract an electron. If it's -2, I would add 2 electrons. Either way, I have 24 electrons to complete the allotment of electrons for everybody. Next, skeleton structure. Okay, we have nitrogen in the center, oxygen, oxygen, and oxygen. Now, let's start adding electrons. This is step number 3. I like to fill the central atom first. You don't have to, but I like to. So 2, 4, 6, 8. This guy is now full. I'm going to give everybody 8, and then I'm going to move on to the next atom. 2, 4, 6, 8. I just keep counting. I don't want to exceed past 24. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. Now, one thing you might want to recognize that I'm doing is I'm adding them in pairs. Electrons are going to be added in pairs. Do not add a single electrons here, single electrons there. Just leads to problems. Now, note that I gave this guy 8, 8, 8, but I could only add 6 electrons to this guy. I ran out. I hit 24. So this guy is short 2 electrons. Now we're going to do the fourth step. What do I do if I'm short electrons? Well, in this case, I'm going to share with a neighbor. This guy here, take them off of the central and add a double bond right here. If I was short 2 pairs, I would need to share 2. This increases from a single to double. Short 2 pairs would increase from a single to a triple. At this point, I'm basically done with my Lewis diagram. A few little things to button it up. Because it has a charge, again, it has a -1 charge, scientists have added this little brackets with a -1 charge listed. Now, we're going to extend this page a little bit. One issue arose from this molecule, or from any molecule of this nature, where as it was being tested, scientists expected to see 2 long bonds and 1 short bond. But, as it turns out, as it was analyzed, they found that each of these bond lengths were equal, and in fact, they were a little shorter than a single, but a little longer than a double. So, their conclusion was that this double bond isn't exactly in this location, or this one, but simply spread out over all 3 bonds. Or you might even say it's flipping back and forth between these. It's hard to say on that level exactly what's happening. But at this point, they're assuming it's flipping back and forth, or a science term for flipping back and forth or vibrating would be to resonate. So, how do you show that this bond is actually in all 3 locations? And they call these resonance structures. Now, a resonance structure is quite simple, and for your typical high school student seems quite monotonous and maybe a waste of their time. But if you have a double bond, or I guess technically a triple bond could work as well, and an identical location where it could have also been drawn, you must show all of the options. That means this guy here, hold my double on top this time, add my electrons, and then I need to do one more where it's going to be going to the other side. There we go. This is called resonance structures. Let's do one more example here, and I'll do one that involves, let's say, a triple bond. And this one is also on your worksheet, but we'll give it a try anyways. Let's go with cyanide, Cn-1. All right, so carbon will contribute 4 electrons, nitrogen will contribute 5 electrons. We need to add 1 more electron for the negative charge, giving us 9, be up to 10 electrons. Make sure it's even. So we'll draw our skeleton structure. We got 2, 4, 6, 8, 10. I have to stop at that 10. And note that I'm short 2 pairs of electrons, so I'll take 2 off of the carbon, another pair, and there we go. You can erase these lines or make sure you visibly cross them out. It doesn't in fact have a negative charge, so bracket with a -1 charge. I don't have any other bonds to flip back and forth from, so there are no resonance structures here. Some students get mistaken and have the atoms rotate. which is not the case. They are much more solid. The electrons, in this case, are the ones that can move back and forth. Let's flip to the next page. And the next page says, okay, how do we know Lewis structures are correct in real life? Example of a Lewis structure including keep in mind, just because we are putting something on paper doesn't mean it's correct. There are a few different ways in which we can draw an E dot structure out that might actually seem correct. You know, just because we put something on paper doesn't mean that it is right. So what happens here is scientists have designed what's called a formal charge. And a very common example of this is the chemical named sulfate. If you were to follow the general procedure I gave you for drawing a sulfate, it would, sulfate minus 2 would be, this guy is going to give me 6, this guy is going to give me 6 times 4 is 12 plus 24, 30 plus 2 more gives me 32 electrons. So in this case, we have sulfur in the center, oxygen, 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 and oxygen. Start adding my electrons. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. All right, so for the most cases, you might think that, all right, I'm done. Put some brackets on it, and it's good to go. Turns out that this, even though convenient to write, isn't exactly the correct structure for sulfate. If you were to analyze this chemical in a lab, you'd find that it is, in fact, a little bit different. You also find it somewhat unique that if you want to write out the formula H2SO4, it's like, okay, well, how would that one look? The sulfate is unchanged. We have the hydrogens basically attaching to the outside of the oxygen. And to me, it makes sense that if every one of these are the same, then how come we only have 2 hydrogens hooking up? Why not have 4 hydrogens hooking up? Turns out that, in fact, these aren't all the same, and the structure looks more like this. We can have our electrons here. There's my last 2. All right. This is the structure for sulfate. And of course, we have opportunities here where 2 of them are double bonded and 2 of them are not. If this thing is protonated to form H2SO4, I'll have essentially a bond coming off of each single bond right here and right here. You'd need to remove these electrons and it would change slightly. But either way, that's the general idea. Now, how do you get back and forth between these and know which one's better? There's a thing called formal charge, and it officially is not on the advanced placement exam, so we don't really talk about it a whole lot in honors chemistry. Occasionally we will discuss it in advanced placement chemistry as a means of basically just discriminating between these two. It's quite simple to calculate. You'd say the number of valence electrons of an atom, like you could do formal charge for every individual atom, and then you would subtract the non-bonded electrons, so this guy has none, and the number of bonds, and therefore 1, 2, 3, 4, 5, 6. So this is not something you can measure in a lab. It's a man-made calculation that allows us to look for the more stable configuration. Again, you would look at formal charge and you choose the one with the smaller formal charge. Like I said, not something that we will deal with in honors chemistry, and as like I said, officially is not on the advanced placement exam, at least as of this date. So that is the general instructions on formal charge. I think that is the end of this little presentation as well. Thank you.